principal investigator. With over a decade of teaching experience, she has contributed to courses in physics, nanotechnology, and battery technology. She is actively involved in PhD supervision and academic mentoring. She also serves as a guest editor and reviewer for several reputed international journals. I request Dr. Desavale sir to felicitate Dr. Manisha Fadtare. Thank you so much, ma'am. Now I request Priyanka ma'am to introduce our next plenary speaker.
Good afternoon, everyone. It is my honor to introduce esteemed guest and speaker of this plenary session, Professor Dr. Jonas Örtegren. He is an associate professor in material science at Mid Sweden University, Sweden. He has been serving as a senior lecturer in physics since 2010 and is a subject representative in engineering physics. He learned his PhD in polymer technology from the Royal Institute of Technology, Sweden. His research expertise spans nanomaterials, advanced optics, and energy materials. With over 55 peer-reviewed publications and H-index of 25, his work has strong academic impact. He has also served as a program manager for engineering physics at Mid Sweden University. Currently, he leads major funding projects on sustainable material and solid-state batteries for advanced application. Sir, we are truly honored to have you with us today. May I now request Dr. A.B. Kakade sir, Dean R&D, to felicitate Dr. Professor Jonas sir as a token of love and respect. Thank you, sir. Sir, the platform is all of yours.
Hello. Hello. Great. Like that? Yeah? Yeah? Good. It's on? Is it on? Okay. It's okay. Yeah, okay, thank you. So I start. So thank you. Thank you for inviting me to speak here. I'm very happy to be here. I will have a talk about sustainable materials for energy storage. My name is Jonas Örtegren. I come from Mid-Sweden University. I will just briefly mention, talk a little bit about Mid-Sweden University, and then I go into research. So here is Sweden in Scandinavia. We are situated in the middle of Sweden. It's not so densely populated. We have two campuses, Östersund and Sundsvall. And at our university, we have about 2,500 campus students in Sundsvall and about the same in Östersund. Some facts about our university. We give almost 500 courses, 60 bachelor's programs, and 40 master's programs. We have more than 1,000 employees and more than 100 professors. And we give international programs. I just list them here very shortly. The ones that are written in bold are international programs. So we have master's program in electrical engineering, engineering physics, computers engineering, additive manufacturing. And we also have master by research programs, which after a bachelor, you do 2 years where you focus on a research project. So you take 3 semesters of doing a research project and 1 semester of regular courses. I represent, well, at the university we have several research fields. I come from the research group Advanced Materials and Processes, so I represent that group here today. We're about 15 to 20 researchers, and we do research in nanomaterials mainly, but the application is maybe additive manufacturing. We do laser processing, fiber lasers. We do nano generators, graphite exfoliation into graphene, aluminum ion batteries, and silicon anodes for lithium ion batteries. So I will tell a story then. I pick one of these research areas that we have, and I'll tell a story about that, and I hope you will enjoy it. So we work with nanomaterials, and as you know, nanomaterials, the properties of a particle changes as it gets smaller. So for example, the color of particles change as they become nano size. They can be both blue, the light can be both blue and red shifted. The temperature, the melting temperature of a material decreases as the particle gets smaller. So metals can melt at room temperature. Here is another property of nanomaterials. When the material gets small enough, the particle gets small enough, it does not crack. And we can see examples of that here from a paper on lithiation of silicon, where as the particle gets small enough, it does not crack. And one can see that schematically in the right picture here, where you have tension in a particle, and the particle would like to crack to release that tension, but then the surface energy comes. And there is a radius to the third and a radius to the radius to the second relation in these two. So when as the particle gets smaller, the surface energy becomes more important, and there is just a certain amount of energy in the system. So as the material gets small enough, cracking has this cracking causes too much energy, and there is no cracking does not occur. Similar reasoning to Griffith's materials theory from 1921. Now we we're making nanomaterials for batteries in this case. If you look at lithium-ion battery, you have 2 electrodes, and you have a cathode and an anode, and the anode is made of graphite. And you see you have lithium ions going back and forth then, during charging and discharging. And the graphite stores lithium ions in between its graphene layers. So you can see here the green lithium ions stored between atomic layers here. And as you see, there is not so much lithium ions there, it's much more carbon. So we would like to have, we want to make batteries with higher capacity. So we want to have better materials. And one such material that is much better at storing lithium ions is silicon. And there is a lot of work going on in companies and at university now to make silicon for lithium-ion batteries. And silicon can store, as when lithium comes to silicon, it forms a new phase. And you can have maybe 5 times more lithium ions than silicon in that phase. So you can store much more silicon, and so much more lithium in silicon, and there's a factor about 10 in between. But the problem with silicon then is that during lithiation, when the silicon picks up lithium, it expands, and then during discharging, it contracts. And when this happens many times, the silicon cracks. There is tension in silicon. But we can then make silicon very much smaller so that it does not crack. There are other ways also of making silicon that's suitable for lithium-ion batteries. One could introduce porosity. One could form composites with graphene around silicon, for example, since graphene does not expand very much. One could improve the binder that holds the particles together. I will first talk about nanoscaling. And here, Manisha Padatare and Rohan Patil, who are here today, they made an invention when they came to Sweden and Mid-Sweden University. They made silicon nanoparticles on graphene in a simple one-pot method, just mixing graphene and silicon powder and PVA and heating this up. And you can see here graphene, that's a black, and then you see small white dots there, that's silicon. And they're so small that they do not crack them during lithiation. However, this was made in one pot. So there were silicon micropowders, silicon microparticles that were heated, and some of them became nanoparticles, but not all of them. So if we run battery cycling and test how much charge this battery can store, we can see what we have with specific capacity and cycle number. And here we have here we have graphite, about 350 milliampere hours per gram. When we have silicon microparticles, that's a blue curve, without treating them, we have cracking of silicon particles, and quite soon we have a quite low specific capacity. But with this method of making nanoparticles, we have a higher specific capacity. But there is a decline there, though. So how can one get rid of that? Well, this decline is because we have both microparticles and nanoparticles there. So after improving the experiment, silicon micropowder and the anode with the graphite was separated, and we found out that one can use hydrogen and heat the sample and form nanoparticles in this way on the graphite in pot B there. And then you have the silicon microparticles in pot A, so you get rid of them. We can do cyclic voltammetry and just see here that when we have graphite only, no silicon, we put on a potential and we look at the electrochemical reaction. We see that we have a graphite peak here in graphite. When we do the same in silicon graphite composite, we have a silicon peak here. So the silicon is active. And then looking at specific capacity as a function of cycle number, we have, if we are having graphite, we would be here. With this method of making silicon nanoparticles on graphite, we are about 50% better than commercial graphite anodes. And interesting to see here also is that the nanoparticles, they grow on the graphite, and after 2 hours they have a certain size and shape, and after 6 hours they are much fewer, but they are bigger. So this is an interesting scientific problem to study. That was nanoscaling. Another way of using silicon in batteries, in lithium-ion batteries, is to introduce porosity into the silicon microparticles. Then there is room for this expansion to happen during lithiation and delithiation, during charging and discharging. And we have looked at how porous silicon is made. It can be made with hydrogen fluoride, which is very toxic. One can do alkaline etching, that is also common. It's also not so good or safe or good for the environment. But then one can do anisotropic etching only. We wanted to do etching in a sustainable and green way. And we used urea-assisted etching of silicon microparticles. So silicon particle with urea, this was heated, and we are looking in scanning electron microscopy to see that we have before treatment and after treatment. We see some porous silicon in the lower pictures there, and non-porous in the upper picture. So this etching is functioning well. And here is a little bit on surface area and porosity analysis. We see that we have around 4 nanometers. We have a pores. We have also pores actually at 30-40 nanometers. We just don't see that here. Anyway, we could identify that with 220 centigrades at high pressure, or at 400 centigrades at atmospheric pressure, we could have a good porosity in the silicon microparticles. And then these particles were mixed with graphene and a binder and made into a slurry, and we coated a copper foil, and we do the cyclic voltammetry again to see that we have silicon, and we look at the black one where there's no silicon, and then we have the red and blue one where we have silicon. So we see silicon is active in this case. And in this way it was possible, we could mix 20% silicon into the slurry. So here again we have specific capacity and cycle number 1 to 100. Here is graphite. Here we have silicon that is non-porous, that's before treatment, and then we see silicon cracks. And here we have our silicon that has been treated with this green etching method. And we have an improvement of about 2.5 as compared to graphite. And it's stable over 100 cycles. If we go into detail a little bit, I'll just mention this briefly. When we add silicon, we want to have as much silicon as possible here, but then suddenly we don't have a good signal here. We have very bad specific capacity suddenly. You see this blue curve here. And with this porous silicon, we have quite a lot of surface, and there are layers formed in the electrolyte that give high resistivity. So one has to solve that in some way. And we have recently used a new binder and the low pH. The binder contains carboxyl groups as in the binder, and then they repel each other since they're ionic. But when lowering the pH, these ones are protonated. The binders are protonated, and they do not anymore repel each other, and they hold together much better. And this binder also forms bonds with silicon. And we see here that we can have a specific capacity about 2,000 for 100 cycles, as compared to 400 for the or 370 for the commercial ones. So we demonstrated a commercial graphite anode that commercial graphite anodes, they have a maximum storage of 372 milliampere-hours per gram. We demonstrated a simple oven method to produce an anode with a storage capacity of 500 milliampere-hours per gram, and reach almost 2,000 milliampere-hours per gram. So much higher than the existing ones. I have very little time. I mentioned we have collaboration with companies, SKF. There are a couple of spin-off companies that come from this research, 2D Fab and Granode Materials. Actually, this Granode Materials actually comes from a patent that was taken by Manish and Rohan, who are here today. They make silicon graphite anodes, and they recently actually got 2 million euro from the state for developing their company. Thank you for listening, and these are some of the people in the Advanced Materials and Processes group. And yes, I think I stop there.
We welcome questions. We can take 2 questions. Anyone who would like to ask questions?
Hello.
Anyone are having questions? Okay. Thank you so much.
This nano silicon material, can it be embedded with any textile material?
If it can be embedded with
Any textile material as a substrate, you can say.
in a textile, yes. It's grown on in this way. It's grown on top of a substrate, so it can be grown on top of textile.
Okay.
Yeah. We go up to quite high temperatures though, so it has to be it depends on the textile, I think. We go up to 800 centigrades.
Okay.
With this method.
That can go up to 800 degrees centigrade.
Yeah, but I mean, maybe one could have a temperature gradient in the oven also, but
Can it be used as the fire retardant then?
Fire retarder. I cannot say really. That's very interesting to see. I have not thought about that, but yeah.
Because many textile materials, they are used in the form of hand gloves.
Okay.
And can be used in some hazardous activities.
Okay. Okay.
So in order to protect them, in case if these type of things are embedded,
Yeah. Yeah.
We'll have to find out whether really this will work out or not.
Yeah. Okay. Yeah, that's a good.
Okay.
That's a good idea.
Fire resistance, yeah, boiler suits and all.
Okay.
Okay. Thank you, sir.
Thank you.
Thank you so much, Professor Jonas. I extend my heartfelt gratitude to all our esteemed speakers for their insightful plenary sessions today. Your valuable knowledge and perspective have truly enriched our understanding. I sincerely thank our participants for their active engagement and enthusiasm throughout the sessions. Your presence had made today's discussion meaningful, insightful. Today's sessions have set a strong foundation for further learning and dialogue. We are truly privileged to have such distinguished experts sharing their expertise. We look forward to equally engaging and insightful plenary sessions tomorrow. I warmly welcome you all to join us again and continue this enriching journey together. Plenary session for tomorrow will start at 10 a.m. At same location, CSE Conference Hall. I request all the participants to join the parallel sessions going on at their respective locations. Thank you once again. Yes. Yes. All plenary sessions are concluded for today. Tomorrow we will again meet for plenary sessions and panel discussion. Yes. Parallel sessions are going on at respective locations. Locations are mentioned in the agenda.